I have the schedule up for 5:23, and I just wanted to mention to you what we're going to do today and what I will be doing over the next week or so. Well, the week after next. I want to continue on today with data manipulation, which actually came from the Data Technologies book, section 9.8. The chapter 8 in our book is called Data Technologies. It ties in some web technologies and specifically some technologies related to bioinformatics. It does talk about some of the same topics, but I think the explanation, what I call data manipulation, in that particular data file is better for explaining the basic operations that you want to do on data, like reshaping data, for example. So we're going to finish that today, and then we may get into a little bit of matrix algebra. I think that it's important that everyone know how to do basic matrix operations, and so in R. So I have a .rmd file that talks about matrix algebra, and it gets into somewhat advanced topics such as the singular value decomposition. I at least want to briefly discuss that. It also has some very simple things. It's basically a review of matrix algebra. If you haven't had it, it's a starting point to learn matrix algebra. Except the nice thing is you can learn it in the context of R, which means you can play with matrix algebra and not just have it abstract symbols. So it may give you, for example, I show you how to solve for a regression equation using matrix terminology. So we may spend a little bit of time on that at the end. I want to start out with matrix manipulation. What I plan to do, I had to have Steve install about half a dozen packages for this chapter 8. So I have to make sure they're working. As I found out in the past, things change and you have to track down the problem. So this week is going to be getting back to chapter 8, and hopefully we'll be able to get the packages, or most of the packages, to work. And then this day will be sort of mopping up any final operations, but I'll also be talking about the final. The final is on 12/17, which I think is a Tuesday night. It's actually from 7 to 9 p.m. Not the best time, but the next day, Wednesday, is actually the last day of finals. So it's not quite the last day, but close. I'm going to go in now and talk about 9.8 from the other book, Data Technologies, and go through. By the way, that's not a bad book to buy if you want to learn about data technologies, but the majority of that book is it deals with interfaces between R and databases. It deals with HTML. There's another book that is coming out in January or February next year. I think I mentioned it to you before. It's called Data and Web Technologies, and I think that would probably be a better book to get. If you wanted a reference book, that's probably what the new book will be in Stat 623 when it's taught the next time. It'll probably be that book by Duncan Tippelang and Deborah Nolan called Data and Web Technologies. I believe it's a Springer book, but it's not out until after the first of the year sometime. You can go find it on their website. You just can't buy it yet. Hopefully it's a good book. I know both of them. Duncan is an absolute genius who is a bit disorganized. Deborah is very well organized, so maybe it's a good team. Maybe I shouldn't have said that. In fact, I'm recording it. Duncan probably realizes that. So we covered part of this, and now I need to go back and I'm going to need this. I'm going to need to read schools back in, and let me be sure. No, I don't have the right directory. So I now have set the directory to be corresponding to this file. So I can cut this off here. And so let's go look at, I'm just going to read in schools. And, you know, we looked at this particular file. This is a fairly big file, and that's the first 6 observations. So we did quite a bit on this last time. These were the schools in New Zealand. Remember, a lot of them were pretty small. There were different types of schools, public, private, etc. So there were different types of schools. We have the city. The authority is really the type of school. And then we have the enrollments. And so we did a number of things with those last time. Sorting and forming tables and aggregations. And now let's go back. The other thing we read another table. We read another table called NCEA, and that had other information. But it actually had some overlap information with the schools data we actually read in. So if I read this particular one, and I look at its dimension, and the first 12 values, notice that these are the same schools, but we have a variable called level 1, 2, and 3 for each of these schools. Now, I for example, could get the mean for those schools for level 1, and I could do that. And on the other hand, you might say, well, I'd like to get the mean for all 3 of the levels. And so I could use the apply function. And if you think about a matrix or an array, or even a data frame that looks like a 2-dimensional structure, I can have the apply function. It's very, very powerful. First of all, I have the structure that I want to apply a function to, and then I have to tell it, do I want to apply it to the rows or the columns? So the margin equals 1 says I want to apply this operation to every row, and then margin equals 2 says I want to apply it to every column. So notice that I subset the data. I said NCA 2 to 4. Well, 2 to 4, in fact, will just give the information level 1, level 2, and level 3. In other words, 2 to 4 is this, this, and this, these 3 columns. And I'm going to get the means on the second margin, which means the columns. So what I'm going to do is I'm going to get the means for level 1, level 2, and level 3. And I can use the apply function to do this. And so if I do that, there are the 3 means. Now if I wanted a range, I do the same thing, except I say that the function is the range. And in this case, we get 2 numbers, the min and the max. Now, the lapply, if I take 2 to 4, I can actually do lapply, and if I do that, I'm taking this data frame. Now remember, a data frame is like what? It's really a type of list. It's a list in which all of the elements of the list are the same length. But the mode of the list could be different. In other words, I could have one. If you think of it as a 2-dimensional array, the first column could be a categorical variable, that is a factor. The next column could be numeric, and so forth. So a matrix, everything has to be of the same. It's a 2-dimensional structure, a matrix, but everything has to be of the same type. Either all numeric, all logical, all character, but it can't be character and numeric mixed together. However, you can mix things by column within a data frame. So a data frame, though, is like a named list, the name being the column headings. That is, the name being the names of the variables. So if I think of a list where everything's of the same length and they all have names, and as long as the type within a column is the same, if it's not, it would be coerced to something like character. But it's a type of list. So the L in lapply means, the L means list. So this is a list apply. So it's treating the data frame as a list, and I'm applying it. I don't have a second argument. It's going to apply the function mean, let's say, to the elements of the list, which are the columns in the case of a data frame. So what this is going to do is allow us, well, actually I'm doing, okay. Did I do, yeah, I did lapply already. So when you do a lapply, it takes the list and applies some function to the components of the list, and it returns a list. So notice that the returns are actually a list with the same number of components, because I'm getting the mean for each component of the list. Is that clear? Now that's kind of not what you want to have, but I'll come back to that in a minute. I mean, it's not neat. I mean, it shows the list structure, but I probably want it more like the one up here. Now I want you to, but I'm going to do now a range. Now notice that again it's a list where again it has the min and the max for each of the three. Now lapply, I've given a simple function here, but this function could be something that you write. You could write a function. That function could be very complex. That function could be very time-consuming. In other words, you could write a function on a very big data set, and every time I apply that function to a particular component of the list, it could be very, very time-consuming. Now, it is very trivial to parallelize lapply. Suppose I have 8 components in my list, and I have a function which is very time-intensive. I could apply L5 to each component, and if I had 8 cores, or maybe 9, because I need a master core plus 8 slaves, so if I had 8 slave cores, I could actually spin out that computation to each core so that they're done in parallel. And then it returns and gets combined back into one result. And I will tell you that it is almost trivial to do that. lapply is one of the principal ways that we do parallel processing in R. It's very common to do it. It is very easy to do it. Now, if you do a simulation, or if you do something that's iterative, where n plus 1 depends on n, that doesn't work. And if I'm doing an iteration, I equals 1 to 1,000, and if 547 depends on 546, you can't. That's not so easy to parallelize. There may be some update operations, but again, in general, that's not easy to parallelize. But if you do a simulation where you get independent samples, then each sample could be analyzed independently in parallel. So a lot of simulations are quite easy to parallelize. Now let's look at the same thing. We're going to use sapply, and suppose I do this. Now sapply is exactly like lapply, except it has one more step. And that step is called simplification, or simplify. It takes the output from lapply and it merges it back. It tries to form it into a matrix or a vector. The S for sapply means simplify. So lapply, if you look at lapply and add one more operation where you try to simplify the results, that's sapply. And here I'll do it for the range. So I get the same results. But of course, you could also use sapply and parallelize it, because it's really just doing lapply. Are there any questions? There's a whole bunch of there's a whole bunch of operations. In a sense, we talked about environments, and an environment is what? It's a key value pairing. It's an associative array. There are different names for it. But if you think of the key as being the name and the value as you could think of an environment as being like a list also, in which you have names for the components. The key is like the name of the elements of the list, and the value in a associative array or an environment, they could be any R objects. So you could have a key value where the key is some name and the value is like a data frame. Or the name could be a list. And then the list is recursive. It could contain list within list within list. So you could recurse infinitely. And so you would ask the question then, how would how do you analyze this type of data? Well, it actually turns out in R it's fairly simple to analyze the data. It's also fairly simple. That was one of the things we were doing yesterday with our software. We were building an inspector that lets you sort of infinitely go down and see exactly what's at each step. To a degree, you can do that in RStudio. But these data structures in R are very powerful, and they're very high level in a sense. Now, in one way, lists, for example, or environments, they're very powerful and they're very useful, but they also can consume time. But R people are clever, and they've learned all these parallelization techniques that, in fact, make things fast. So the apply function, the reason I mentioned this is an E-apply. E means environment. So there's an apply function that applies it to the elements of an environment. There's a T-apply. We've talked about T-apply. That's what you call a ragged apply. So if you have if you think about a list which is of different lengths, or you have components that are at different lengths, and you want the mean, like you have a one-way analysis of variance, but the number of observations in each group is different, and I want to get sums or means. Well, you can do that with T-apply, because it's what's called ragged. It's like N1, the number of observations in the first group is different than N2, different than N3. So I have different number of sample sizes in each of my groups. No problem for T-apply. It doesn't require that, like a data frame where they're all the same length. It doesn't require that in T-apply. So T-apply is another one of the family members of the apply family. There are a few others. You might also guess as P-apply for parallel apply, but
is it the only one that's parallel?
No. You can use L. There are lots of variations that allow for parallelization. Now, if I have, when we teach 624, we go into that in some depth. 624 is called high performance analytics, and there's really three topics in that course that we covered the one time I've taught it. One was parallelization for doing high performance computing using parallel processing. The next was using technologies called Hadoop. Hadoop is the way that most big data is analyzed. And so, by big, I mean really big. So big that you cannot begin to store it. You can't, you can store it, but you distribute it in a distributed database, and you do parallel processing, and it's what's called a map, but you have a map phase and a reduce phase. And a lot of statistics boils down to a map phase and a reduce phase if you look at it in a logical structure. So we look at this. We look at this for very, very big problems. This is what Facebook and Google and all the big data companies are doing. This is a big technique used for data mining, where we can combine Hadoop with data mining techniques for massive data sets. And then the third topic we talk about in that course is streaming data. That's where you have like sensors. So you have a whole bunch of sensors. You're collecting data in real time. And this is done now. It's becoming ubiquitous. It's going to be you're going to have sensors. Like if you think about these watches that are going to come about, they're going to be collecting data from all over your body constantly, and you're going to be potentially, and it will talk to like a smartphone. And so you're going to get alerts. Better drink some water, getting dry, which I am. So in other words, the age of sensors is coming. And it would be very nice if we had the age of sensors so that we didn't have to do to do biopsies, for example, or to do, if you had nanobots running around your body. I'm beginning to sound like Ray Kurzweil here, but you have nanobots running around your body and constantly monitoring things, various levels. Now, Ray Kurzweil kind of goes berserk, and he takes like 200 pills a day because he's so concerned. Well, he's convinced that the singularity is near and we're going to live forever, and he wants to get to that point. So he's a little far out. He was hired by Google, so we'll see what happens. But at any rate, there was a recent Time magazine article that said, "Will Google conquer death?" It's a little optimistic, I would say. But at any rate, that may be Ray Kurzweil's project. No, it is really a medical project they're working on, not really conquering death, but to extend life. At any rate, what was I saying? What was I talking about?
P-apply.
What now?
P-apply. Parallel.
Oh, yeah, okay. The third part is on, I was talking about sensor data, streaming data. You could have how are you going to have self-driving cars? Well, you better have a lot of sensors and monitors out there. You know, these plane wrecks, the pilot was saying last night that when I fly from New York to London, I only touch the steering wheel 7 times. And that is because the computer flies it. But you better know what to do. Some of the most recent crashes have been because it's automatic, but then something happens and all of a sudden the plane takes a nosedive, and you better have well-trained pilots then. So you can have sensors doing things, and you can have sensors driving cars, but, you know, I'm not sure we would totally want to remove the driver. But my point is that sensors will become ubiquitous. And that means we're going to have streaming data that's ubiquitous. So how do you analyze data where you cannot store it? You cannot store it. It's too big. It's too massive. You cannot store it. If you talk to the astronomers over in physics, they're getting this pulsar data, and some of our people are working on it. It's flowing in petabytes, so massive and constant and continuous that you cannot store it even. So you have to analyze it in real data, and that's what I mean by streaming data. It's so big you can't even store it. So you have to do it in real time, and so how do you do it? And that was the third part of that course. But at any rate, it's a very fascinating topic, and there are different ways we can approach it. The way I approached it in this topic was called extensible Markov models. Markov models is something you learn in stochastic processes, and you have these different states, and you have transitions between the states, but typically the states are fixed, whereas in dynamic models, the states can come and go, and the transition probabilities between them constantly can be updated. And so that's one type of model that we can use. And you can actually look at using graph theory, you can look at these graphs and how they change over time. And this could be a gene interaction network within genomics, or protein interaction network. You could look at how things are changing over time if you had sensors that could actually measure this. At any rate, let's continue on. It's an interesting topic. That's simple. So why am I doing it? Well, we're merging. You already know how to do a simple merge. That's a simple merge. I can get a collection of 1 to 3, 4 to 6, and it merges the two together into a vector. Very simple merge, right? And I can C-bind. That's another type of C-bind. Binds by column, so that forms 1, 2, 3, 4, 5, 6. So that's another type of merge. That's simple. And an I-bind combines by row. So we have simple merges. But suppose I want to merge schools with NCEA where they have a common key. This is the kind of thing you do in relational databases. So what I want to do is merge schools with NCEA, and I have a by. In other words, I have X and Y. The X refers to this schools, and the Y refers to the NCEA. By.x equals name, and by.y is name. So I'm going to merge. They both have something called name, and they're the same. So I'm going to merge the two data sets together. Now, the one data set is much bigger than the other, but it's sort of going to fill in. And so I have all.x equals false, and all.y equals false. So let's sort of see what we get when we do this. So if I analyze this, and I'll look at the head. If I look at the head, what it has done is merged the two data sets, that it has the level data combined with the school data and the authorization and enrollment. It now also has the level data. So the merge operation is extremely important. Now you have to understand that if you're in JUMP, for example, you can point and click this, but we can program it. So it can be part of our workflow to merge, and there's a lot of other things we can do too. So we have the capability of doing these operations as part of a workflow. I could just say, in this case, there's a default action. If I just say merge the two, if there's a default match, it just sort of does it. This is a little bit dangerous because if I just say merge the two, it turns out that I get the exact same thing in. That's because I only have one column that actually merges. If you have exactly certain matching columns, it will merge it will take default actions. But in general, you got to be careful about using the merge and having it make assumptions about how you want to merge it. But in this case, it works. That's because we have a relatively simple structure. So this is the merge. If I look at the dimension of Auckland schools, maybe I should. Is that the merged one? Yeah. It's 86 by 9. So notice, because I didn't keep all the information, it just merged the relevant information from the schools, and it didn't have the schools that were not part of the NCEA data set. Now you could merge it, and when I said all equals false, all dot x equals false and all that, well, if I said true, it would be a much bigger matrix, but it would have a lot of blanks, missing data in it, because it would just be merging what you have. And in the case of one, I only have 86 observations. So you can play with those different options depending on how you want to merge it. So there's a lot that you can do with the merge, but it's a very useful thing, to learn. Now, splitting. If I say I want to split enrollment by authorization, I can do that. And if I do that, by the way, you should learn the structure command, str, because that structure says that I have a list of 4. And these are the 4 components. And notice that it says that other is an integer. It says 1 observation, 51. Private is an integer, 1 to 99. These are the first group of, notice that has dot, dot, dot. So that's the first group of observation. Then I have state integrated. So this tells me it's a list with 4 components, and it tells me how many are in each component. And now I can apply to that, and again I get these observations. Now one of the most important things that you're going to be doing is reshaping a data set. Reshaping is a very, very important operation. So if I look at the head of NCAA again, if I look at the head, the problem is that for a lot of statistical models, I don't want level 1, level 2, and level 3 being horizontal. I want them being vertical. If it's a factor, say I have a factor that has level 1, level 2, and level 3, then I need them vertical for most linear models that we would be doing. And so there's a library called Reshape. There's actually another library called Reshape 2, which has some enhancements and changes, actually. Long NCEA, this means I want it in long format. And I use a function called melt, M-E-L-T. And I'm going to melt NCEA, and the measure variables, measure.var is 2 to 4, which are the level 1, 2, and 3. Now look what happens when I do this. And let me print out the first 6. So what it does is it stretches out. Notice that the values, notice that the values are sort of now stretched out. I have all of these, then I'm going to have all of these, and then I'm going to, if I went far enough, I'd reach level 2 here and level 3. So it's stretching the data out in that way. Okay. Now, I could equally have well, instead of saying measure.var is 2 to 4, I simply could have also said that the ID variable is name. And so that's the ID variable. And I would get exactly the same result if I do that. So if I look at it, I get the same result. That's just 2 different ways Sometimes it's more convenient to say the ID variable, and sometimes it's more convenient to list the variables that are actually being stretched out. So I'm back to 264 by 3. No, I'm sorry. No, I'm not back. This is the long format. Originally when I had 86. Now CAS goes the other way. It goes from long to wide format. So if I take the long format that I've already created and I cast it, it will take it back. There should have been a simpler way to remember which way Milton cast. I always forget it. Which is which. It's not very intuitive. There should be some intuitive name that means wide and long. At any rate, if I cast this, that takes it back to what I had. So if I cast the long version and I have name tilde variables. So the way I did it, if you look at the long version, I have name tilde variables. It's like a formula. And that will give me back to the wide format. I could also, let's see. Oh, I didn't save it. Yeah. Oh, suppose instead of name tilde variable, I say variable tilde name. What do you think that looks like? The dimension, the dimension of this is 86 long, if I would print out the whole thing. But suppose I say cast long NCEA variable by name. That's just the opposite. Here I said name. This is what I want to do. But what would happen if I reversed it? It's like doing a transpose of the data. The rows become the columns, and the columns, in other words, the rows become the columns. So actually it stretches you have many, many, many columns, like 86 or whatever. But so if I do that and I look at the data, I'm only printing out the first 6 columns because I said 1 to 6. So I have the level, and then I have the schools going across this way for level 1. And if I look at the dimension, it's actually 3 by 89. Why is it 89? Well, you get this. I'm not quite sure how that comes out, but at any rate, that's like doing a transpose of the data. So if I took the cast, and instead of doing name tilde variable, I do variable tilde name. It's like taking the transpose. Now, if you look at jump, for example, they actually have a method of taking a transpose of the data. So if someone gave you, for example, if you have gene expression data, the way that I talked about expression sets at one point, and I said expression sets, the actual expression data is stored, not the columns actually represent the columns actually represent the observations or the patients or subjects or whatever, and the rows actually represent the genes. Now we think of the genes as being variables, so instead of typically our data is an n by p matrix or an n by t data frame where n represents the observations and p represents the variables. For the genomic data, it's p by n, where the genes are represented by rows and the data is that is the observations are the columns. So if I wanted to transform one to the other, I could do it with this method. I can in effect take a transpose, although there is a transpose function. So, okay, any questions on that? Well, moving along, we have a case study here. So we've sort of looked at some pretty powerful techniques. We've looked at the apply functions. We've looked at merge. We've looked at reshaping, either long to wide or wide to long. So we'll take an example, which is and I forgot to put this in for you. I apologize. I will do that. There's some Baltimore data set, and maybe I should show you what this data set looks like. So what we have is a start date, and then I think these are gas meters or something. And then we have I'm not sure what the term. I think there's a heat thermal units or no?
Kilowatt?
Well, the kilowatts is later. Then we have gas use, kilowatts, electricity, temperature, days. I need to look this up a little bit better. This is why you need these self-documenting data sets like in your packages where you click on it, you see exactly how every variable is defined. That's the data set that we're going to analyze. And so, first of all, I'm going to read this in. We'll call it utilities. It's baltimore.txt, so apparently the data was collected in Baltimore. We'll read it as utilities, and then here are the first 6 observations. Notice that the first observation is a date, and so this is another thing that you haven't had, and I want to take a look at this, is, well, how do we analyze date data? So it's over time, so we should be able to say, well, this date's later than this date. We should know something about how time works, and in terms of analyzing it. Maybe you want to plot by time, whatever. So this is our data set. Now what we're going to do, first of all, is reformat. We're going to reformat the date that's here. So let's run that. So I'm going to replace utilities. I'm going to take utilities.sort and reformat it in this way. And so I'm coercing it to a date with this particular format, and I'm replacing it. In other words, I have utilities $start gets as date coerced the original format, which is the first column, and I'm going to format it as date. The B is it's a format that's used. You might say, well, why isn't that date month year? Well, this is a variation of that. And so I do that, and I see, okay, it's of class date. And then if I look at it now, you notice that the format is different. It is year, month, and day, but at any rate, we've changed the format. Now, what I'm going to do now is I'm going to break the dates into 5 categories. So I'm going to form breakpoints, and so the starting date point will be the minimum of the dates, and then I'm going to take 10/99/07/31, in other words, July 31st, 1999, and I'm going to coerce that. I'm going to coerce all of these into dates, and then the next breakpoint will be 2004, April 22nd, and the next one is April. The next one will be September 4/1, and finally 2005, 12/18. And then the final one will actually be the max. So I'm anchoring it by the min and the max, and then I'm breaking it. There are 4 internal points that I'm breaking it. So if I take the data and form these breakpoints, so let me make sure I get the whole thing. So I'll run that. And let's take a look at the breakpoints and see what they are. So those are the breakpoints now. And so remember the cut function. I think we talked about this earlier. We have a cut function. So I want to cut utilities.start by breakpoints, and I want to include the lowest, and I don't want labels. So we'll call this phase. And so if I do this, and if I look at phase, I've now converted the data to, in essence, a factor. And so I have 1s, 2s. These are the numbers. These are the categories defined by these breakpoints. By date, and so this is a date. And now suppose I want a sum of all these variables. I want to aggregate now based on the phase, and I want the sum. So what do I get when I do that? So I'm going to get phase sum, and then what does that look like if I run this? Whoops. what's happening. And this is interesting. Yeah, there. Let's see if this works. Yeah. So now, what I'm getting is for each of the 5 phases, I'm getting the sums of kilowatt hours, the sum of days, and so forth. So in phase 1, there are 406 days. The total kilowatt hours used is 5883. The total amount of gas used is 703.27. Okay. So this is very interesting because we took a date, we split it up, and we were able to summarize by these break intervals. Now, suppose you want the average amount used by day. So I have more days here, so I'd like to know what is the average by days for these 5 phases. So I could say phase, I'm going to look at 2 to 5. I don't want 6 because that's days. So I'm going to divide by phase sums $ days. So if I do this, I now get the average amount. I get the average amount. Notice I rounded. I said significant digits is 2, so it's rounding off to 2 significant digits. And so that gives me the average amount used per days for each of those 5 phases. Are there any questions on that? Now, I could have done this by the sweep operator, and that's another powerful operator. And so what the sweep operator says, I'm going to take the phase sums, and I'm going to do margin 1. In other words, I'm going to do it by row, and I'm going to sweep out using days using the function divide. So it means actually I'm going to divide each row by the day for that row, the number of days for that row. And that's exactly equivalent to what we did before. So if I actually analyze this, well, if I printed it, I would get exactly the same thing, but, well, in other words, phase sweep is exactly the same, except I didn't round it off here. I didn't round off, but it's the same. So the sweep operator, notice that I could have I could sweep out by column if I wanted to standardize the data. If I take the data and I want to standardize it by, say, subtracting out the mean of each column from the column, then I could use the sweep operator to do that. So the sweep operator is pretty powerful. So it's another one of these functions that you can put in your bag of functions that can manipulate data. Table. So here I'm looking at months of utilities, and if I do this, I'm forming a table. And what I'm doing here is I'm looking at the months for different phases. I have utility start. I'm looking at months corresponding to utility start, and by phase. I'm doing a table where I'm looking at utility start by phase. So utility start by phase, a two-way table, in other words, and I'm labeling this by month.name the rows. Okay. So I didn't label the columns because it's okay to use this 1 to 5. If I do a billing months, if I look at if I look at a factor, if I look at utility start with these levels and I make it into a factor with months, I get what we'll call billing months, and then we could aggregate the sum over months. It's a similar thing for all of these. We could get the sum over months using aggregate. And in this case, let's see. So I have months, and I'm going to, in this case, I'm going to look at months, and I'm going to look at the significant digits for months that I computed up here. And let's see what that gives us. I didn't finish. Okay, and so that gave us by month the summary information. So the point being that you can take these, we took a data set and we were able to summarize it. if you learn SAS, there's one of the big reasons people use SAS was because you could actually do what was called report writing. And so every month, every month you get new data and you want to generate these reports automatically. So you write code. The point here is that it's probably even easier to do that in R than in SAS. Now in JUMP, the report writing capability allows you to write textual information around the report. Now I would reclaim that if, let's say, you want to publish this report on the web as a report that your supervisors can look at, how would you do that? Well, I would recommend that you would use R Markdown. You embed the R code in it, you generate reports, and you can have all the kind of discussion you want about the various tables that explain what that table means. You know, that I'm getting these summaries by month, but you could explain this, and so if you embedded this type of R code into .rmd files, you could create HTML files that could be published on the web. You actually can embed R code in other environments. You can actually embed there are special people who have allowed you to embed R code within Word documents or within spreadsheets and so forth, or ODF documents, and of course you can use SWeave to create PDF documents. So there are tons of ways that you can write reports using R. So this is something that if you were analyzing data, these are simple summary statistics. There's nothing highly statistical about this. You're just getting summary statistics. But if you had to do monthly reports, this might be an approach you would take. Okay, so you might want to review some of these materials. Okay. Any questions? Okay. How much time do I have? Okay, I'm just going to briefly show you this matrix algebra stuff. We won't get to do much today. And I don't know how much I'm going to leave this up to you versus where did I put it? I didn't put it in this chapter. I'm not sure where I put it. I probably should just put it out here, but I do have it in the other course that I'm teaching. So if I look at 512, I'll put it over in your notes. You can download it. It's there. Oh, I think it's here. It's called Matrix Algebra. And here's the file. And let me reset the directory now. Okay. So let me knit this so you can get a gist of what I've done. So I start out very simple. I define a matrix. Let me blow this up a little bit so you can read it. So I define a matrix that has n rows and n rows and an n column. So that's an n by m matrix. And we sometimes denote it by just a sub ij in brackets. And so that's a basic matrix. So what might this be? So by the way, as I go down through it, I start out kind of simple, like matrix addition, and then I get in matrix subtraction, scalar multiplication, matrix multiplication. This is an incredibly important operation. Then I get into transposition or transposing, matrix inverse, and certain properties of inverses, and how you do it in R. I try to illustrate most of this in R. Submatrices of a matrix, determinant of a matrix, which if you have a 3 by 3 matrix is easy to compute, but it becomes increasingly difficult. By the way, you probably didn't realize that if you know anything about a determinant of a matrix, it's actually represents the volume. If I think of a matrix in terms of variables, and if I think of a certain operation on those variables, it turns out the matrix is the volume of the parallelepiped of the data. And it's a good indicator of singularities in your data. And singularities correspond statistically to the word collinearity. So if I have a collinearity, meaning one of my variables is written as a linear combination of others, if I have a collinearity, then that's not good. It can mess up like regression models. So at any rate, the determinant actually helps you locate singularities among other things. And here's some properties of matrices and block matrices. These are special types of matrices. And then I get down, I have lots of examples here. And ultimately I get down to vector algebra, which talks a little bit about vector spaces if you want to review this. And this talks, but this topic right here, I would say a huge amount of statistics can be done with these matrix decompositions. Anything in linear statistics and certain types of nonlinear statistics can be done with these decompositions. So for example, in the LM function in R uses the QR decomposition to do regression. If you do linear models and regression, the QR decomposition, and I say it as if there's only one, but in fact there are many QR decompositions. You may have heard of one of them called the Graham-Smith decomposition, but there are others like the Householder. And so there are lots of QR decompositions. Some are more efficient for various types of problems, but regression has done that. Another type of decomposition is the LU decomposition, where L is a lower triangular matrix and U is an upper. And then one of the most important topics in stat is the singular value decomposition, and it underlies a lot of the multivariate techniques. And then the eigenvalue decomposition, if you've done eigenvalue analyses, again, if you were studying both singular values and eigenvalues, if you're studying collinearities in models, then these are the principal tools you use to do that. And square root decomposition, can I find a matrix that if I can I decompose a matrix to, what do I mean? Okay, the square root of 4 is 2, right? 2 times 2 is 4. So if I have a matrix, how do I have, what is the matrix that I multiply it times itself? I get the original matrix. Well, only certain types of matrices you can do that. And then the Cholesky decomposition. So these decompositions are extremely important. Let me just show you a few things. If I define a matrix A, I can use the matrix command. And I've said I want a matrix A. And I want 3 rows and 3 columns. So the 3, 3 means 3 rows and 3 columns. So what does A look like? Well, I'm going to name the rows. This actually has to do with moose vegetative areas in Montana. And so I have bulls, cows, and cows with calves. And these are moose bulls and cows. And I'm going to name the variables. It's called V1, V2, and V3. And that's what my matrix looks like. So I have bulls, cows, and cows with calves, and I have 3 vegetation variables. So that is my matrix A. So I formed it with the matrix command. Now suppose that that's being done in 1958, and suppose I do it again in 1959, and I do the same thing, and there's B. So I have 2 matrices now, 1958, 1959, and I could ask, for example, I want the sum of those 2 matrices, and that gives me the sum, and that, whoops, well, I didn't want to do that. I wanted to skip down to here. This gives me the difference of the 2 matrices. And I better quit. At any rate, that's some very basic matrix operations. We'll look at this a little bit more. You should know this stuff. Depending on how far you're going, things like the singular value decomposition are absolutely essential. Okay, I'll stop. Oh, I'm actually stopping too early. I'm thinking it's over at 2. 2:15. I'm going to go on. I almost gave you a break. So it's It's actually been a long day already today. Okay. So yeah, I'm still recording. Good. I almost did it. Yeah, so let's, let me knit this again to sort of see where we are. Maybe I should let you out a little bit after I got you all set to leave. Basically, if I do scalar multiplication, it simply takes every element of A. If a C is a constant, it takes every element of A and multiplies that element by the same constant, C. But matrix multiplication, now that's a little bit different. Matrix multiplication says, if you can tell what's happening here, I'm doing inner products, and if you scroll on down to where I talk about inner products, if I have a vector x and a vector y, and I take the inner product of x with y, it's just the sum of the x sub I, y sub i's from I equals 1 to n, and I'm assuming those two vectors are the same length. So I take x1 and multiply it times y1, and add it to x2 times y2, and add it times x3 times y3, all the way till I get to the end. And it doesn't matter whether I do, but that prime, x prime, means transpose. So if x is a vector, then to transpose it, if x is a column vector, meaning it's n by 1, then if I transpose it, it is a row vector, which is 1 by n. So when I talk about the subscripts, or if I talk about the dimension, the first subscript will represent how many rows. The second subscript will represent how many columns. So when I say x prime y, x prime will have 1 by n, and y is n by 1. I multiply corresponding elements and add them together, and that is called the inner product. Well, matrix multiplication is just a whole bunch of inner products. So if I go back and look at if I look at this, suppose I take, I need to give a little more detail here, and I'll add to this, but suppose I take the first row of A and multiply it by the first column of B, and I take the inner product. So suppose A11 is the upper left element, and A12 is the first row, second column, and A13 is the first row, third column, and A22 is the diagonal element of the 2 and 2. A21 would be the second row, first column, and so forth. And likewise B. B11 is the upper left, B12 is the first row, second column, and so forth. Suppose I take the first row of A, and now I'm going to assume that for this to work, the number of columns of A must equal the number of rows of B. So I say the number of columns of A must equal the number of rows of B. That's because I'm going to take the inner product of the columns of A with all of the rows of A with the columns of B. So if I take the first row times the first column, that will give me a single number, which in the matrix is the upper left. If I take the first row times the second column, I get the 1, 2 element of that new matrix. If I take the first row times the third, I get the 1, 3. If I take the second row times the first column, I get the 2, 1 element, and so forth. Is everyone clear on that? Now, so what is the dimension of C? If A would be n by m, and B would be m by p, then what is C? It would be n by p. It would be, you would take the first dimension of A and the last dimension of B. If you think about it, you'll see why that's the case. So suppose we have the number of U's having lambs in 1952. I ought to update this, I guess. The number of lambs in 1982, 52, and 53. And so we're looking at the 2 years, and I'm going to form a matrix A. Should need to go back here. So let's form a number A, and I'm going to name the rows. Row names of A is none, single, and twins. Columns are none, single, and twins. And let's look at A. So 52, 1952 would be the corresponding to the rows, and 1953 corresponds to the columns. Okay? So what does this mean? There were 58 U's that had no U's in 52 or 53. Following? There were 26 that had no lambs in 52, but there were 26 of them that had a single lamb in 53. And there were 8 U's that had no births in 52, but 8 in 53, and so forth. The next row would be that there were 52 that had no births, that had single births in 52, but no births in 53. So for the matrix is not symmetric. And you keep going, and there were 9 that had twins in 52 and had twins in 53. Okay. Now suppose that I want to count how many lambs there are in 1953. Then I could do 0. I could create a vector called 0, 1, 0, 1, and 2, meaning 0 births, 1 birth, or 2 births. So for a single, it's 0. For none, it's 0. For twins, it's 1. I'm sorry, for single, let me start over. For none, it's 0. For a single, it's 1. And for twins, it's 2. Now I'm going to now form this matrix B. And so that's B. And I'm now going to multiply A times B. And let's see what is C. I'm going to name it to 1953 total. And if I do this, how did I get this? I mean, how did I get the 42? Can anyone tell me? I'm matrix multiplying A times B, where B is a vector. Now, R is smart enough, if you say, well, it's a vector, but it looks like it's a row vector, but R is smart enough to say, okay, if I matrix multiply, then I have this sort of vector, but I have to make it like it's a column. And R just does that automatically. So I'm multiplying this matrix times the 0, 1, and 2. You can think of it you can think of this as A times this column B. So if this is a 3 by 3, and B is a 3 by 1, what is A times B? It'll be a 3 by 1. So it's a 3 by 3 times B, which is a 3 by 1. Take the first element, the 3 by 3, that's a 3, and the last element of B, which is a 1. And so how did I get a 42? Well, I multiplied 0 times 58 plus 1 times 26 plus 2 times 18 and added them together. That's 42, right? Then the second, that is the 1, 1 element. The 2, 1 element takes 52 times 0, 58 times 1, and 12 times 2, and that gives you 82. So I'm actually doing matrix multiplication. And then the last one, if I take 1 times 0 plus 3 times 1 plus 9 times 2, I get 21. So that's a simple matrix multiplication in R. Any questions? What is the transpose of A? Transpose A multiplies, it interchanges rows and columns. So look at the matrix. So if I compare A to the transpose of A, if I compare this matrix to the transpose of A, what does it do? It interchanges the rows and columns. So the first column of A is 58, 52, 1. That becomes the first row of the transpose. Any questions on that? Now, so let's take a look. Let's take a look at matrix inverse. So what do I mean by the inverse? So if I have 2, what would you call the inverse of 2? Well, what do we mean by an inverse? Suppose you say, if I take a number and I want to multiply it by another number so that it equals 1, then the inverse is what we call reciprocal in the case of scalars. So 2 times a half is 1. A half, that's a reciprocal of 2. 1 over x. So if I have x times 1 over x, that will equal 1, unless, of course, x is 0. If x is 0, you have a singularity. I've used this word several times today. So if you're a physicist and you think about a singularity, what do you think about? What do you think about a black hole? Well, mathematically, that has a certain meaning. Here we have a singularity because what is 1 divided by, what is 1 divided by 0? So, it's infinite. You can think of the limit, 1 divided by epsilon, where epsilon is going to 0, that's going to infinity, right? Now suppose you have a matrix, and I need to define the concept of an identity matrix. So what corresponds to 1 in the matrix language? It's what we call the identity matrix. The identity matrix has 1s on the diagonal and 0s on the off diagonal. So it looks like that. 1s on the diagonal. Let's say the I sub n means it's an n by n matrix. It has 1s on the diagonal, 0s off the diagonal. That's the identity matrix. Suppose I said I have a matrix A, and I'd like to know if there's a matrix that I can multiply A times that matrix and get the identity matrix. That's sort of like doing a reciprocal, right? If I had a scalar, x times 1 over x equals 1. So I want the corresponding thing. Now, one of the things you should note is that A times B is not necessarily equal to B times A. In fact, they may not even have the same dimensions. Okay? So what happens? If A is 4 by 3 and B is 3 by 4, I multiply them together, it's 4 by 4, right? But if A is 3 by 4 and B is 4 by 3, I multiply them together, it's 3 by 3. So, it's usually the case that AB is not equal. It's not commutative. That AB is not equal to BA in general. It can, but in general it's not. So suppose I say I want to find a matrix B such that A times B is equal to the identity matrix. If we can find such a B, then B is said to be the inverse of A. And we call it A inverse with this symbol right here. A inverse, like a superscript. If A inverse exists, then A is said to be non-singular, and otherwise it is singular. Now for those of you that have done linear models, you get, when you have a linear model, let's talk about where we have the analysis of variance, but we have more than one factor. So we have like A by, in R notation, we have like A plus B plus A colon B, where A colon B is the interaction between the A and B factors. Now if you were running R, it would turn out that if you had a model matrix, you would have a vector of 1s for the intercept. And if you had small a levels of A, you would have A dummy variables. And if you had small B levels of B, you would have B dummy variables. And if you have A colon B, that would be A times B. The problem is that if you have dummy variables defined in each category, those A columns add up to the vector of 1s, and therefore you have a singularity. Likewise, the columns for B, the dummy variables for B, add up to 1, and therefore you have a singularity. And you have lots of singularities for A colon B. Therefore, that matrix, the rank of the columns, which I haven't talked about rank yet, that's later, is greater than, the rank of the columns is less than the number of columns. If I multiply that, transpose of that matrix times itself, that's called the X prime X matrix. That is singular. Now, the way R does it, it puts a constraint on the model. When you did the one-way analysis of variance, you would say, okay, I have mu plus alpha sub I plus epsilon sub ij, and I have a constraint. The sum of the alpha sub i's equals 0, or alpha 1 equals 0. Unfortunately, RSS and jump all do it differently. You need a constraint, because if you don't, you get into a singularity. Jump uses sum of the alpha sub i's equals 0. By default, R uses alpha 1 equals 0. By default, SAS, that sets the last one to 0. They all use a different constraint, but it really doesn't matter because you have to reduce you have to get rid of the singularity. And so if you tried to do that, you would have a problem. Now, SAS has a procedure called proc-GOM, which doesn't get rid of the singularity. And what it does is it gets something called a generalized inverse. But R doesn't, or at least by default. So R reduces the dimensionality so that you don't have a singularity. But how do you find singularity? Well, if you can't get an inverse, you have a problem. And that corresponds to things like the determinant being 0 and so on and so forth. At any rate, so how do we get the inverse? That's an aside. But if you're doing linear models, it's kind of important to know these things. So if you're doing analysis of variance or covariance or multiple regression, in regression it doesn't happen as much because I don't have these dummy variables. But you can. But if you're not smart, and you say, okay, I'm going to measure exam 1, I'm going to measure exam 2, and I'm going to put exam 1 plus exam 2 in there, you have just introduced a singularity by putting the sum of the two you already have in the model. You don't want to do that. Okay, so I have a matrix A. I have A above someplace. Where did I find it? Okay, here's A. What's the inverse of it? Well, that's really simple to do in R. You simply say solve A. Now, solve actually has two arguments, A, comma, something else, like a Y, and that will solve a system of linear equations. But if you only have one argument, it will simply take the inverse. So solve of A is the inverse of A, and so the inverse of A is this matrix. Now, if it's truly an inverse, I should be able to matrix multiply A times that matrix and get back what? The identity matrix, right? That's what I said. I said that if you take A times B, and B is the inverse of A, then it will equal the identity matrix. So I said that B is the inverse of A. Let's see if it is. So I'm matrix multiply A times B, and I'm going to round it off to 5 digits, and I get that, which is the identity matrix, right? 1's down the diagonal, 0's off the diagonal. So I have found the inverse. Now, suppose I had some properties up here, and that first property says, if the prime means transpose, that says A inverse prime is the same as A prime inverse. So what does that say? It says the order doesn't matter. I can inverse and then prime it, I can inverse and then transpose, or I can transpose and inverse. It's the same answer. So the order of transposition and inverse does not matter. The second condition says that if I take the inverse of the inverse, I get back the original matrix. It's like taking, think of 2. The reciprocal is a half. Now take the reciprocal of a half. All right? So you notice that here I'm going to take the transpose of solve. So here T means transpose. I'm going to take the transpose of the inverse here, and here I'm going to take the inverse of the transpose. I reverse the operations. Solve T. Here I have T solve. And notice they're identical. So I illustrated that the order of operation does not matter. By the way, these should be square matrices. Okay. How am I doing now? Oh, I'm not letting you out very early. So, at any rate, a submatrix is a submatrix. It's like in R, I point out the 1, 2, 1, 2, pulls out the first 2 rows and columns, and gives a submatrix of A, which pulls out this submatrix right here. So you could pull out any submatrix using these operators. Okay, we'll stop here. You might want to look at this. We'll do a little bit more here. Again, I feel that it's important that you understand the power of R for doing matrix algebra. And you may not realize it, but actually R can do calculus up to a point. I'm not saying it competes with Mathematica, but